Hello everybody and welcome to Unit 10. This first video is on exponential functions, focusing on just exponent rules and then exponent graphing. And the reason we're starting with exponents is because this unit is mainly about logarithms, which you'll learn is really are exponents. So you're going to hear me say a lot that logarithms are really exponents and exponents are logs. And I just felt like I absolutely had to do this unit because if you think about the word logarithm, L-O-G, it's pretty much within my name. So I think it's meant to be that I take Unit 10, which is all about logarithms. And so before we start this video, 10.1, I would like you to pause and write down what do you already know or remember about exponential functions. So think about what an exponential function might look like. Think about what it really means to you. So please pause the video now. So while the video was paused, I wrote down a few things. What do I already know about exponential functions? So I wrote that you could grow or decay. I wrote that exponential could mean to rise or fall quickly. And I also wrote down a couple graphs that some of you may recall from past classes that you're either rising quickly or falling quickly. So you could have really anything along those lines, which brings me to a great second question to consider. Would you rather have $100 a day, or would you rather have 1 cent the first day, and then that 1 cent doubles over time and doubles every day for a month? So think about that. If you start with 1 cent, that means the next day it would double, the next day it would double again, the next day it would double from there. And I want you to consider, and I'm going to have you pause the video again, consider how much money you would make in a month, and let's assume that a month is 30 days. And then also consider how much money you would make if this is continuing to double for 30 days. So as you're thinking about it, I'm going to pause the video and write down some things that I found, and we'll compare when we get back. So please pause the video now. All right, so I bet many of you figured out if you made $100 a day and your month had 30 days, you would make $3,000, which is a decent amount, but definitely not as much if you would make if you started with a cent and doubled it each time. In fact, if you take a look at the blue numbers, well, the black numbers represent what day we're on. I didn't go all the way up to 30, but I really don't have to choose which one's better because I've keep doubling each time. By day 10, I'm already at $20, and then by day 20, I'm at $20,971.52. And so what's interesting is if I kept going all the way to 30, and then I added up all of the amounts that I had from day 1 to day 30 in 1 month, my total would be $1,073,418.23. So the answer is definitely I would like to start with 1 cent per day. But what's interesting in the comparison of these two things is if you think about this relationship in red, this is really a linear relationship because every day you go up the same amount. However, this relationship here is more exponential, which we mentioned before means that you're rising quickly. And so even though you're starting with a much smaller amount, if you're doubling over time, this exponential logic is going to get you a lot more money in the end. So definitely option 2. The next thing we want to do is just define a couple things for an exponential graph. So an exponential function really looks like f of x equals b to the x, where x is really the power and b is really the base. And there's some restrictions on the base, and here's why. So the restrictions on the base is that b has to be bigger than 0 and cannot equal 1. Here's why. If b equals 1, what we really have is f of x equals 1 to a power. And if you think about it, 1 to any power, 1 to the second, 1 to the third, 1 to the fourth, is always going to get you an answer of 1. And so this relationship is not exponential because you're not rising or falling quickly. And so that's why b cannot be 1. Okay? So I'm going to write a little note. 1 to any power is 1. So if b has to be greater than 0, let's consider why b cannot be less than 0. So let me give you an example. If your base is less than 0, that means it's negative. So what if I did negative 2 to the x power? If I started plugging in values, negative 2 to the first gives me negative 2. Negative 2 to the second gives me a positive 4. Negative 2 to the third gives me a negative 8. Negative 2 to the fourth gives me a negative 16. So some of you might have already noticed the signs keep flipping, and that is also not an exponential relationship. So because we keep going from an odd function to an even function to an odd to an even, because we keep going from negative to positive to negative to positive, that's why b cannot be less than 0, because it has a situation that's not exponential, and that's why that b cannot be 1. So b cannot be 1, and b cannot be less than 0. That's why this restriction is there. Something else that's extremely useful before we really go into logarithms is recalling properties of exponents. And so again, what I'd like you to do for a minute is I would like you to pause the video, and I would like you to write down any of these exponential rules that you remember from your Algebra 2 and Algebra 1 days. So please pause now, and I'll come back, I'll unpause and go through them. All right, so in purple, there are my exponent rules from the Algebra 1, Algebra 2 days. So feel free to pause the video at any time and copy them down if need be. But what I'm going to do is I'm going to write specific examples of each underneath just to kind of get you to remember what's going on. So here's an example of b to the x, b to the y. If I give you 2 to the third times 2 to the fourth power, because the base is the same of 2, if you have 3 2's here and 2 4's here, what you really end up doing is adding the exponents. So it would be 2 to the 3 plus 4 power, so your answer would be 2 to the 7th. If instead of multiplying the bases, you're dividing the bases, for instance, if I stuck with the base of 2, 2 to the 8th divided by 2 to the 5th power, that would really be the same as 2 to the 8 minus 5 power, or 2 to the 3rd, or if you wanted to simplify that further, just the number 8. Now the reason it ends up being subtraction is because 2 to the 8th really means 2 times itself 8 times. 1, 2, 3, 4, 5, 6, 7, 8 2's. Then I'm dividing by 2 to the 5th, or 5 2's. 1, 2, 3, 4, 5. And if I have the same base on top and bottom, I'm allowed to cross them out. So you can cross out 1, 2, 3, 4, 5 pairs of 2's, which leaves you with 3 2's or 2 to the 3rd, which is why the subtraction rule is applicable. Anything to a negative power does not give you a negative exponent. It actually instead causes a reciprocal. So if I gave you something, again, sorry about the room here, but if I gave you something like 2 to the negative third to relate to the last problem, 2 to the third is 8. So that means that this would really be 1 over 2 to the third, or 1/8. So whenever you see a negative exponent, it really causes a reciprocal, not a negative number. Anything to the 0th power in math is 1. So, to again stick with the base of 2, if I add 2 and even x to the 0th power, all of that would just be an answer of 1. What this property is saying is that anything to the first, like 2 to the first, is itself. This power, ab to the x, is really the same as like 2 times 3 to the x, that you could say instead of 6 to the x, this is really the same as 2 to the x times 3 to the x, because the power is applying to both bases. These two powers, these two properties, the first one and this one right here, are the most mixed up two. If you, though, think about what this means. If I give you 2 to the third and I raise that to the second power, the reason we multiply the exponents is because 2 to the third squared really means 2 to the third times itself, which based on the previous rule would be really 2 to the 6th power. So if you think about the original problem, what could you have done more quickly to get the 6 rather than writing out twice? You could have just multiplied the exponents, which is why that rule is applicable. The last exponent property, a to the x, or a divided by b to the x, is the same as if I took 3 over 2 to the x power. Both of these bases or this exponent applies to both of these bases, so you could rewrite it as 3 to the x over 2 to the x. So instead of doing the graphs on this video, I would like to instead start a new video with exponential or graphing exponential functions. I think it'll be better for you studying later. So please pause now and start with me on the next video, part 2. Thank you.